Hey everyone. Yeah, I'm ready. So I'm also going to share my screen and present a YouTube video because we did this demo before and this will be a little bit easier, but we'll be here for Q&A or you can just email us as well after. Very high level, we are presenting Polybase is a ZK layer 2 rollup to Ethereum with private USDC transactions. That's the first application we're building on Polybase. And one of the key features of it also is that we have compliance proofs for AML using zero knowledge proofs. So you don't have to reveal any of your transaction data. You can just produce a proof that shows that you haven't interacted with any bad actors. So let me share my screen and get started there. All right. Cool. Welcome, everyone. Today, we're going to do a brief demo of Polybase. Polybase is a layer 2 ZK rollup for private transactions. Specifically, today, we're going to demo two of the most important features of Polybase. The first one is private USDC transactions. This is not possible today. So any USDC that's transacted today is public forever. Obviously, that's a problem for a lot of use cases that businesses use USDC for, including payroll, B2B transactions, trade finance, and even remittances for consumers. And so we're going to show how we can do that basically for the first time ever on a public network. And the second is compliance proofs. So we're going to show a mechanism for generating AML compliance proofs on private transactions. Again, something that hasn't really been possible before. And we have built this network from scratch and written the ZK circuits from scratch to be able to do both of these things. Callum, go ahead and scroll down. So just a quick, really simple overview of what's going to happen in the demo. We have two participants, Bob and Alice. They both are going to have wallets on Polybase. Bob is going to send Alice money, and then Alice is going to generate a compliance proof that proves that she hasn't interacted with any bad actors. We're going to have a Polybase node running that's going to be both a sequencer and the prover. And then we're going to roll up to Ethereum, where we have a smart contract deployed for verifying the proof generated by Polybase.
Great. Yeah, thanks, Sid. You're going to carry on.
Yeah, okay. And so I'll just give a quick overview of all the different steps we're going to take. So we're going to start the rollup server. That's the Polybase node. We're going to create two wallets. We're going to mint some test USDC to Bob's wallet. We're going to make a private transaction from Bob to Alice, and we'll see some of the steps that happens when we do that. Then we'll generate that compliance proof, and then we'll actually ban Bob's address, and then Alice will generate another compliance proof, and we'll see how that fails when Bob's address is banned. So Callum, let's kick it off.
Cool, yeah, thanks, Sid. So the first thing I'm going to do is start the Polybase server, because the clients will need to interact with that when submitting their proofs. And then I'm going to create the wallet for both Bob and Alice. So on the top left, I've got Bob. So I'm going to create his address. And you can see I've created a wallet here for Bob. This is the address. This address would be similar to a MetaMask or Ethereum address. And this allows people to send money to Bob. It works in a very similar way. And we can create a wallet also for Alice. And you can see she's got an address as well, which is different to Bob's address. Okay, so then I'm going to create some mint some USDC for Bob. And what this is going to do is it's going to send a transaction to Ethereum. Effectively, this will be bridging money into the network. So it would lock the money in the original form. It would mint it on Polybase. I'm going to submit that transaction. And you can see I have the note here, which is really just another way of saying it's the transaction that's occurred. We have 100 USDC here, and we have Bob's address here to say who it's from. And then we also have the source address, which is the same as Bob's address. And that source address remains consistent across many transactions. So any transaction that derives from this transaction would still have the same source address. And that's important for compliance, which we'll talk a little bit more about later in the process. So the next thing we want to do is just send a transaction from Bob to Alice. And this will be a private transaction. So Bob is going to have to create the entire proof that he needs to ensure he's compliant. And then he can send that off to the prover. So to do that, I'm going to say Polybase transfer Bob, and we're going to send it to Alice's address. I'm going to send the 100 USDC. And so here we have the zero knowledge proof being generated. That's been generated in 1.5 seconds. It's it's often thought of that ZK proofs are pretty slow, and we've worked really hard to get this down as much as possible. We're pretty proud of being able to get it down to kind of around a second on commodity hardware. And we've only got a 16 kilobytes size here, so we can kind of send this from a mobile device, a browser, a network bandwidth limited device would be able to send this proof. And this proof has all of the private data mixed into it so that all that needs to be sent to the prover is the proof itself and a hash. So transactions have been added to the rollup mempool, which we can see there's stuff happening over here. I'm going to go through that in detail in a moment. But that transaction was sent to the prover, and the note was sent to the receiver. So Alice received the note to let her know that that money is incoming. And as soon as it's committed to Ethereum, she'll have that money.
And I just want to mention something here, like the proof is generated on the client side. And so it's pretty amazing that we're able to generate that ZK proof on the user's computer, on an app or in the browser. And that's what allows us to keep the transaction data actually private to the user, but then generate the proof and send it publicly, like Helen mentioned.
Yeah, exactly. And so again, now we have a new transaction or note being generated for this new note for Alice or transaction for Alice. It's gone from Bob's address to Alice's address, but notice the source address still remains as Bob. And we keep that trace across all transactions, so that will remain as Bob's address throughout any other transfers that would occur in this process. So I have the group, what's the aggregate kits, and I can kind of, this is something that we're going to continue to work on. While that's running in the background, I just wanted to kind of show you the diagram so you've got a high level view of what's happening on the network, and I can kind of explain where we're up to in the process. So the client here, you can see this client is, for example, Bob. There could be many other clients on the network. All of those transaction proofs are bundled by the rollup prover. And as Sid mentioned, all of the private data is kept on the client. The prover only receives these proofs. That one proof is sent to Ethereum. It verifies that proof. And then once it's verified the proof, it updates through hash. And that enables all of the people on the network to independently verify that that has happened. So it looks like this proof has gone through. And just to kind of follow this through step by step, we have the proof being sent to Ethereum. We have the transaction of the proof being verified on Ethereum, and we can even look at Etherscan and see the transaction being applied to Ethereum. So now Bob knows, you can see here on the left, we know that the root hash has changed. We've got a new block that's been created in this new root hash. And Bob's now confident that the note did get sent to Alice, and Alice could do the same check. So let's jump ahead and have a look at Alice's balance, and you can see that the money has indeed gone up over to Alice, and we can check Bob's balance. Bob wants us to check that generate a ZK proof on the client. She checks the compliance, and then she can also generate a ZK proof on the client to prove that that source address or the transaction or the note that she has is a valid note, and that's done by checking the source. So just to explain that in a little bit more detail, I've got a diagram here which kind of shows what's happened so far. We have Bob minting the note. That note was sent to Alice. And this is the process of her creating and checking the OFAC list or any other list that would determine whether you're a bad actor or not. And she's able to create a proof that Bob, this source address Bob, was not included in this OFAC list. Notice that she's not checking for Bob. So she's not checking the note specifically, she's checking the source. And she's proven that the source of this note was not from a bad actor because Bob is not a bad actor. And the only thing that's required is the proof to be sent to either Ethereum or any off-ramp like Coinbase. And they just need to look at the proof in order to know that the note that Alex has is compliant, and then they can pay her out her money. So again, we're hiding all the details and just sharing the minimal information that is, this is a transaction that is allowed. And now for an example, let's see what would happen if for some reason Bob was actually a bad actor on the network. We can simulate that process of adding here, Bob to the list. So I'm going to do that here. So I'm going to ban Bob's address. So now this address has been banned. If Alice was to try and create a ZK proof to prove that her transaction is valid, she obviously can't do that because the note is not compliant anymore because of the banned source address.
Cool, I'll stop it there.